Hello, how's it going? Hi. Hi, my name is Amanda Hinchman-Dominguez, and welcome to A Brief History of Memory Leaks. Okay, this talk is inspired from the newly published O'Reilly publication, Programming Kotlin with Android, Achieving Structured Concurrency with Coroutines. When Pierre and I wrote this book, it was our hopes to provide a solid foundation on Android fundamentals to ensure proper practices around structured concurrency, and to show readers how Kotlin has evolved Android development by giving historical context needed to be able to fully appreciate the problems that Kotlin solves in Android. So we're at an exciting point in history, watching how Android and Kotlin evolved together ever since Kotlin had been adopted as the official language for Android. It's been really amazing to watch Kotlin and Android bring out the best in each other and, like any relationship, challenge each other a little bit to become better. So, how many people know about memory leaks? Okay, all right. So I'm just going to get kind of like a gauge here. It's going to help me give some good context. So how familiar are we with like the basics of memory leaks? Raise your hand if you feel like it's kind of solid. Okay, that's all right. It's a-okay. Don't worry. Memory leaks are a really hard topic. There's no need to convince folks of that. And frankly, there's not a lot out there on memory leaks. You can kind of find it in tidbits and scattered about. God, Lord knows I've tried looking, so. Today, we're going to look at Kotlin and Android as a case study to learn more about the nature of memory leaks. A walk down memory lane, if you will. Okay, so 2017, there was the Kotlin Conf, and JetBrains came out with coroutines, and the general message was, coroutines are like lightweight threads. Then in 2018, there was a fun talk from Roman Elizarov for coroutines in practice, and he actually came back and he's like, okay guys, coroutines are not exactly like lightweight threads because they carry resources. And then, of course, in 2019, he actually started introducing the idea of structured concurrency to create just kind of like safer practices around some of these issues. To understand why structured concurrency had been coined, we need to understand like a little bit of the context here. So the Kotlin team made a desire to create thread-bound UI programming for Kotlin coroutines. And when coroutines were designed, the mindset was kind of, Kotlin does not have any standard APIs to work with resources and does not define any resources in its common standard library. So all resource-working APIs are for the JVM only and are based on JVM resource management designs. So structured concurrency was introduced to create safe design against memory leaks and coroutines, and we'll get to that later. So when exactly did we start talking about memory leaks? I started digging, and I found an obscure blog all the way back in 2009 from the Android developer blog on avoiding memory leaks. And then there was not too much on it until maybe about 2016 for the Google, I think it was the Android developers YouTube series, Perf Matters. Would highly recommend it. I think it definitely helps me become the Android developer I am today. So I looked on the Kotlin side as well, and memory leaks, of course, have popped up over time. I did find one fun kind of issue, KT1622, that was filed where the coroutine does not clear internal state. This was kind of fun to read because at first, some of the JetBrains people were like, I'm pretty sure this is how it's supposed to work, but over time, they found out, okay, it is a memory leak. It was fixed in Kotlin 1.4. The point is, memory leaks are everywhere. They're in your apps, they're in your IDEs, they're in your phones, and we're gonna keep creating them, and we're gonna keep finding them and fixing them. They are everywhere. So, what is a memory leak? I like to take a conservative definition on this. So, a memory leak is when the heap holds to the allocated memory longer than necessary. So this could include leaking references for scheduled work and concurrency. There's also another definition, a memory leak can occur when an object is allocated in memory, but it's unreachable for the running program. So one example of this could be passing Android components outside of main threading. And another important thing to remember about memory leaks, you can write memory leaks, but your dependency can also have memory leaks. Your Android code, the OS itself, or sorry, not the OS, the API, the Android API framework, can also have memory leaks. So the relationship between memory consumption and power consumption in Android is symbiotic. The more memory that is freed from allocation, the more power it requires from the device. So when a device is low on memory, battery drainage can become a concern, or worse, bad user experience. Memory also affects the ability to kill and quickly resume applications. Why do memory leaks matter? This is always an important question. I know sometimes it's kind of a tough sell, you know, when you're talking to a product or something like that. But it does matter. Application quality depends on user experience. How well is your application working? Is it working fast? Is it working efficiently? And something to remember is that Android has very limited resources and hardware capacity. In many ways, iOS and Android has become rather comparable and very competitive in terms of software, but we know that iOS continues to kind of hold supreme over their hardware. So we have to be very conservative with how we use our resources. It's really important for us. And something to consider is that roughly 15% of Android users in the world still uses Lollipop and Blow on their devices. So, and also, when you have memory leaks, it can cause jank, out-of-memory issues, and other strange behaviors. And while it is true that you see less memory-related issues on your devices, it's important to ensure your app is accessible to users with lower memory on their device. So it's the developer's responsibility to do everything in your power to manage processes to be able to minimize power and memory consumption. Water break. Okay, what do you need to know to catch memory leaks? You need two things. You need to understand how a self-managed memory environment works, and we need to understand the limitations of the Android threading system. Okay, one of the beautiful things about Android development is its self-managed memory heap and the garbage collection mechanism it uses to free allocated memory back to the heap. One of the perks of a self-managed memory environment is that we don't need to worry about overhead when objects are created and destroyed. However, this doesn't mean that it doesn't happen at all. So a self-managed memory environment depends on its garbage collection mechanism. So, heap and garbage collection. Every application has its own process in heap. If your app reaches heap capacity and tries to allocate for more memory, it will receive an out-of-memory error. Garbage collection frees the allocated memory back to the heap. It's smart enough. It usually will do it if it can find data objects in the program that cannot be reached in the future. And it also reclaims the resources used by those objects. Objects that are eligible for garbage collection, nullifying object references, reassigning object references, and objects that are created inside methods. So jank can also occur if one is not careful with the kind of objects that is held in the heap. And if you have something that's if you have a heap that's really, really full consistently, then you're going to end up having a ton of garbage collection getting initiated. It can actually pause your main thread, and it can stop more than just your application. So it gets kind of ugly. So as part of the equation, we also need to add the complexity of the limitations of the Android system in tandem with the JVM environment. So some characteristics of the Android threading system might surprise you. Consider the following scenario where a user clicks a button in an application. When the user clicks a button and an action is started, a service starts, and the service starts running, then the thread system will not necessarily create a thread. It actually starts on the main thread. It's your responsibility to send longer work to a background thread. And then, of course, return the results back to the UI to prevent blocking the UI thread. So some other characteristics of Android, there's some really important ones. With many, Android is an event-based application, so of course there's like the main thread, there are your background threads. Your UI components are intended to be in the main thread. Your interaction should be in the main thread. Let's see, are there any other all components run within the same process? Yep, so we covered a lot of these items. And then, of course, storing references to Android components in the background thread can cause leaks. We're going to get into that a little bit. So you can get two kinds of memory leaks. There are implicit memory leaks and explicit memory leaks. An explicit memory leak can be a little bit easier to spot. You can spot it by eye and code reviews. They are easier to catch. So here's an example of an explicit memory leak. I definitely don't do this, where we have a static reference to a context that's saved. And it's not just context, it's also context, activities, fragments, views. Do not save them statically. Yeah, what ends up happening is static references end up getting stored in the heap and then just never garbage collected. These objects are pretty big, please don't do it. There's actually another memory leak talk tomorrow where I kind of go through Cookbook of things to do and not do. So definitely check that out. There's gonna be more of these examples in that other talk. Also, I'll try to pay attention to phones, you know, like if I see people, sorry, I might have been clicking through a little fast. Okay, let's talk about implicit memory leaks. Implicit memory leaks, it's a little bit harder to find. A lot of this has to do with implicit referencing. We're gonna get into that as well, but in general, using Leak Canary can catch these. That's just kind of like the easiest thing to run with. I think it's the most practical. And it's, of course, I know we mentioned that you can write your own memory leaks, but your dependencies and your libraries can also have memory leaks. So be wary of these, because like I said, they're a little bit harder to catch. Okay, we're going back to this little timeline. This is kind of a fun one. We're going to get into async tasks because it was deprecated in 2019. And until that point, it was the most commonly used Android data threading primitive to send a task to a background thread. And despite its good intentions to enable easy multi-threading in Android, its most common uses were for integrating results back into the UI, which often ended up causing memory leaks, missed callbacks, and other unpredictable behaviors. So, for example, there's an inner class extending an async task within some activity or fragment. And the thing is, when you have an inner class, it's going to hold an implicit reference to the parent class, meaning that in this case, we have like an async task running, there's some kind of background thread, but the whole time, it's still holding a reference to the activity in this case. So this is a problem. If that main activity is destroyed, an implicit reference could still be held in some async task should the thread be running for any reason at all. The heap would end up holding this reference, and it ends up clogging up your heap and even garbage collection if it ends up having to clean it up, or ends up trying to clean up multiple times. So memory leaks that are permanent are obviously very bad. But if we revisit our very conservative definition of memory leaks also occur when a reference is held longer than necessary. This is a debatable topic as to what that could mean. But I am going to bring up an example that Pierre and I did side with on PY for this one. This was just kind of maybe a famous example of a hotly debated topic in terms of memory leaks. So, not clearing view references in a fragments on destroy view call, if you have references or member references to views, listeners, and you don't like nullify those references on destroy, those views will be retained using the backstack. This might not be a big deal for smaller applications, but larger applications would end up having those small leaks accumulate, and that stuff just really builds up. So this is a screenshot of PY's answer to this. This is a reference to the issue tracker in regards to this issue. And as you can see, I'll read it up here. So the kind of like the results where the status was won't fix, it is intended behavior. For some time, I don't think they had it in documentation, they might have it now. The fragment's view, but not the fragment itself, is destroyed when a fragment is put on the backstack, and that is working as intended. Leak canary requires that you null out references to views when onDestroy view is called. While this is technically not a memory, or technically a leak, because it eventually gets cleaned up, Leak Canary has chosen to treat it as such. If you have a large application, you should be doing the same thing. You need to be very conservative with your memory if you have a lot of data to work with in the first place. Okay, review. How's everyone doing so far with memory leaks? Cool, thumbs up, we're doing great. I'm so happy. This is going well. So, memory leaks occur when the heap holds on to allocated memory longer than necessary, or the references become unreachable. And there are explicit memory leaks and implicit memory leaks. And now that we've had our short crash course on memory leaks, we're going to level it up. There is yet another kind of implicit leak that we haven't quite talked about. As Roman famously puts it, there are 3 categories of programming bug complexity. There are simple bugs, hard bugs, and concurrent bugs. So, why is concurrency so hard to manage? Well, callbacks rapidly become complex and hard to maintain without thoughtful design. You need to be able to account for listening to lifecycle events if you're not careful about stuff like that. Again, I take a little bit more of a conservative approach for interacting with the Android UI components. Definitely check out that other talk. But also, when you're working with concurrency, there needs to be a thread-safe way of being able to interrupt those threads. Okay, imagine that you're developing an application to help users plot, plan, track, draw, and share information about hiking. Your users should be able to navigate to any of the hikes they've already completed or are in progress. So, in this hiking app, we have a call on hikes fetched, and we're gathering the following data: total distance, length of last hike in both time and distance, current weather, and favorite hikes. That's a lot of different data, probably coming from different places. In Android, that could be done in a number of ways. Java, of course, has the traditional thread library and the executor framework. The Android standard library has async task, now deprecated, handler thread, as well as the thread pool executor class. Okay, so in situations where a single background task might take a long time to execute, you need to work with more than just one background thread. A thread pool executor lets you spin up a number of threads and toss that work onto blocks of work to execute, and it gets managed for you. So we're going to take a look at a little bit more code. Now we're just kind of like showing a coding solution for this. So you'll see here that we do have our executor service, and then on hikes fetch, we're feeding in the data of hikes, and you'll see that there is an IO thread pool. And also we have like a runnable handler in here. There's a lot going on. So inside a view model, suppose you use one of the factory models for the executor service. From the executor class, you get back a thread pool executor, and you're performing asynchronous work using your traditional thread-based model. In the following code, we've chosen a work-stealing pool. So compared to a simple thread pool with a blocking queue, a work-stealing pool can reduce contention while keeping the targeted number of threads active. And the idea behind this is that enough work queues are maintained so that an overwhelmed worker might have one of its tasks stolen by another thread that might be less loaded. So, some pros and cons about all this. This is a solid implementation, don't get me wrong. This is thread safe, since only one thread owns the state. There's relative ease of callbacks, it's pretty readable. Cons. Using a thread pool can be overkill, especially if you don't invoke fetch hikes for user for different users concurrently. So, it's kind of like using a sledgehammer for a nail. Again, it comes back to Android having only so many resources You can only spin up so many threads at once, so make sure you really know what you're doing. So this is fine. This is fine. What about memory leaks? Well, we've already addressed a lot of potential areas already. You'll see that there is like the shared state, like it is not within the threading, it is outside. And then there's also, let's see, the runnable. But there is one misconsideration, that would be cancellation. So this is where things could go wrong. So with mutable data, thread confinement does prevent this. You have your mutable state living in one thread, that's great. You're making sure that your runnable handler is not accidentally left open. And then, like, we have this whole cancellation thing. What exactly is that? Well, we're going to go back to the Android threading model for a little bit. So there are additional complexities to working with threads. Some important characteristics: devs cannot control when a thread finishes. There is a cancellation mechanism that you can technically do, but I think the easiest way to think about a thread and its life cycle is, okay, a thread starts, it does some work, and then when that work finishes, that thread dies. That is how it works. If that work doesn't finish, the thread will never die. So, oh, yes, and of course, if you're unable to control when a thread finishes, in some cases, it becomes really hard to control your execution flow. And so if one is failing, the others are still going to run. And this isn't great where we have like our work stealing pool and one failed and now everything starts clashing because some work got incompleted. It gets kind of messy. So this is why we don't inject anything with an Android lifecycle into a thread, since the reference to the object will be held even if like the original reference has been killed, whatever. So also, some other important things about Android threading. In threads, exceptions are not propagated. They will get swallowed. Android designers have made the choice to also crash the app if there's an unhandled, uncaught exception handler as a choice to make it fail fast. This is good for Android, not so good for app developers who want to keep customers. But there is some good news. Cancellation mechanisms are much easier in coroutines. If you're writing threading with coroutines, you should make sure that they are cancelable because you can do it for free. Coroutines does not require threading data primitives like handlers to pass the data, and there's safe cancellation mechanisms, which is actually encouraged for coroutines. So let's revisit the original problem of our onHikes fetched, fetching the weather and, all that information. We have all those APIs coming in, and we also have wind, temperature data, whatever. So if a crash is thrown, all the coroutines are still there. So this is similar to the behavior of running multiple threads, like one crashes, the other ones are still running. Normally, we catch this exception at the top and try again. But we spin up another set of child coroutines, the same thing happens, and the remaining coroutines are still running. So this is what Roman was talking about. This is how you can get memory leaks even in coroutines. However, this is why we want to be able to implement coroutines that are able to automatically cancel dangling background threads to reduce the risk of those memory leaks. Okay, so I know we started talking about exceptions. Might be helpful to cover what kind of exceptions there are. We started talking about unhandled exceptions. There are also exposed exceptions. So these are the only kinds of exceptions that can be handled by client code with try-catch, and then unhandled exceptions typically makes your application crash, or at least recover, and then kind of leave your app in an undetermined state. Not too great. So if you don't handle the exception, thread uncaught exception handler will be evoked. So great news is with coroutines, if you kind of have like an all else fails backup plan, which is you have your last chance to catch these unhandled exceptions by registering it as a coroutine exception handler. I'm just going to call it CEH for ease. So this stops exception propagation and helps to avoid a program crash. A coroutine exception handler is conceptually very similar to the thread uncaught exception handler, except it's intended for coroutines. It's a context element which should be added to the context of a scope or a coroutine. The scope should create its own job instance as a CEH, only takes effect when installed at the top of the coroutine hierarchy. And then also a really nice benefit that you get on top is registering a custom handler will also kind of give you like a custom, like, it will also give you the ability to print those exceptions right in the stack trace. So you no longer have those like swallowed exceptions. It's quite nice. Okay, so now, if this crashes, the exception is caught by the scope, and the scope cancels all the child coroutines that it already launched, and then it exposes the exception. So you need kind of like 3 parts for this. You'll see that you need to register a coroutine exception handler with a launch. So the launch must be the coroutine root builder. And then you also need a scope. The coroutine scope expresses uncaught exceptions, but it also notifies its parents. It waits for launch completion before cleanup, and it doesn't leak jobs, so that's really nice. Then you also have like the supervisor scope. There is one crucial difference, because there's also coroutine scopes. The difference between coroutine scopes and supervisor scopes is that it only propagates the cancellation downward and cancels all the children if it has failed itself. Okay, so we talked about memory leaks with coroutines a little bit. We talked about implicit leaks and how they are generally pretty hard to catch. Luckily, most of these, like even explicit ones, explicit and implicit, can all be caught with Leak Canary. Makes your life so much easier. I don't have any sounds, let's see, but I do have a video. Let's see. Okay, so this is a TrekMe app, kind of like in relation to the example we were talking about. I know that's the Nexus. I got really lazy. Like I had all my other emulators filled up, and I was like, whatever, I'll just do this one. Yeah, so I made fetching tiles from, I made the task of fetching tiles abnormally slow. If you can, oh no, it's so blurry. But this is actually a fragment where on destroy, I had actually uncommented out some nullifying references to some particular views. So this is kind of referencing that, oh, it's technically not a memory leak. So if we run it, okay. All right, so the idea, you go to creating a new map, you choose USGS, you wait long enough to see the tiles start to appear, so you can see, oh, kind of disappeared, so it's starting to render. But then you rotate the device several times, and eventually it's going to make Leak Canary cry. That poor thing is just trying to catch up. Oh, there it is. All right. Leak Canary caught it. So MapView has internal threading and uses like some kind of tile provider to fetch tiles. And then of course, when we rotate, onDestroy view is evoked. And then because we had commented out the mapView.destroy, the background threads are ultimately still running. And then those threads have an implicit reference to the map view itself. And unfortunately, I didn't show the whole thing. One of the nice things about Leak Canary, if you don't use it already, once you have it configured in and it's like, okay, you see that, you can actually pull down the notifications from your system tray, and it gives you like exactly the stack trace where you need to find it. So if you don't use memory leak, or if you don't use Leak Canary, first of all, like make sure you have a conversation with your team about it, because you know, sometimes addressing memory leaks, like people kind of panic over stuff like that, and it can be kind of a tough conversation to have, especially when you find out you have a ton of memory leaks in your application. Yeah, come to tomorrow's talk, because I think there's a lot of low-hanging fruit that can be addressed, and it doesn't have to be as scary as it can be. So yeah, memory leaks, it's been tough, like going from company to company and then kind of like realizing that sometimes, you know, I mean, I was writing Android for a few years in before I started learning about memory leaks, and then I realized I'm like, oh no, I've been putting in memory leaks. Like, I better fix all that stuff. So it's kind of a humbling experience. It do be like that. So some lessons. Avoid potential memory leaks. Watch how you interact with your Android API framework. I think a good way to kind of think about what you're doing, like, hey, am I interacting specifically with anything in the Android API framework that might include hardware stuff? You know, like we're talking about like cameras. We're also talking about like services, anything like that. So if you have like Android API stuff just like sitting in a background there, I'd Android UI related components, like just watch for that stuff. Make sure you're following the constraints of the Android threading model. Make sure your Android UI components stay in the UI main thread. Profile your code with Android Studio. Actually, let me hop back for a minute, because something else that I did not point out, you'll see that I'm running Android Studio, but you'll also see that in Android Studio I have the Android profiler running. It's quite useful. It is a little slow, but it does allow you to drill in. There are other tools that you can use as well, but this is a good place to start. You can actually kind of like record it, and it'll break down everything by Java, native, whatever you need. And it is quite useful when you want to go hunting for memory leaks. OK, some other stuff. Yeah, ask yourself, could I be interacting with a hardware component, databases, networking, Android graphics, location, et cetera, et cetera. Oop, going the wrong way. OK, pay special care to your static references, since they are stored forever in the heap. So never store Android components like activity, service, view, et cetera. Do not reference activity, view, fragment context, and other Android components outside your UI thread. And use glide if you can, if you have to work with bitmaps. And if you are using bitmaps, this is kind of the same as nullifying your references and listeners. Make sure to recycle your bitmaps. Reduce, reuse, recycle. And of course, if you're working with services, take a careful look. I know like services is kind of always a less fun topic, but it can be a source of major memory leaks. You have to really know what you're doing when you're working with services. So for example, like let's talk about like bounded services. If you bind, a bounded service lives for as long as all the components it's bound to live. So if one of those components don't die, the bounded service is not going to die. So if you if you bind multiple components and then and you just forget to shut one down, it's just going to run forever. So be very careful with your services. OK, that is all that I have for this talk. I know there is a lot of stuff in here. But if you're interested in learning a lot more about some of these topics, kind of like in greater depth and at a pace that you feel a little bit more comfortable with, there is the programming Android with Kotlin book. It's kind of funny. There's like really only like 2 sections of memory leaks, but all that's in that book is kind of like what you need to like understand why these memory leaks happen. So if you want to learn about the Android threading model, thread safety strategies, thread cancellation mechanisms, structured concurrency, coroutines, channels and flows, it's all in there. OK, I think that's everything. Thank you so much. Does anyone have any questions for me?